Yep.
So when is your final?
Tomorrow.
Okay. So what's the last stuff you want to cover for this semester?
I just review. I finished our packet, so I'm just trying to find something else.
Yeah. If you want to give me subject matter, I can maybe find some problems. Although it's better if you do. But if you've already done all of the problems in your book, then that can be difficult.
Yeah, I've already done all these, so maybe start with zeros, finding zeros and using them to graph.
Okay, zeros of quadratics, zeros of polynomials, third degree polynomials, fourth degree polynomials.
I think the last one was third degree.
Okay, let me see if I can find a few. But you have done P over Q or not?
Yeah.
You have, okay. Let me start off with this one. How are we going to do this? Always look for the easy way first. Before you think about doing it the hard way, is there an easy way to do this?
I'm not sure.
You want to check the relationship between this coefficient, which is 1, and this coefficient, and see if it's the same ratio as that coefficient relative to that coefficient. And it is, which means that it can be solved by grouping. Okay, so knowing that it can be solved by grouping, what should I write next?
I don't know what the grouping thing is.
Okay, here's what I'm going to do. I'm going to group those two numbers together, and I'm going to group these two numbers together, and then watch what happens. Now, I want to put these in a parentheses, so I have to alter it slightly in order to make sure that I get the plus 18. I got to put it like that. Okay, now I can factor an x squared out of that. So it goes to and I can factor a 9 out of that. And now, what can I do from that step there? Think factor. you're used to factoring out single terms, but it doesn't mean we can't factor out binomial terms. In other words, that divides evenly into this term and this term, and that's all we need. As long as you have a term that divides evenly into both terms, you can factor it out. That's what I'm factoring out. What's left over?
Nothing.
Huh?
Nothing.
No, when I factor it out, I'm dividing it into each term. So x squared times x minus 2 divided by x minus 2 is what? In other words, this is what's left over. Minus 9.
Okay.
Now look at this very clearly and make sure you understand it, how I got that. And what more can I do? In other words, this isn't fully factored. What is x squared minus 9 called? How does this factor?
X minus 3.
And
X plus 2.
so those are the three factors. So what are my three solutions?
2, 3, and negative 3.
Yeah. And that's how you solve cubics that can be grouped. Now, obviously, that's going to be a very small percentage of cubics, but I'm going to go with that's what I would focus on. In other words, is all I have to do is change one number here, make that a 7, and I cannot solve this by grouping. Not only that, it becomes particularly difficult to solve when I have to use P over Q. Although, let's take that problem. How would I attempt to solve this using, obviously grouping isn't going to work. And there really aren't any other techniques for cubics. If it can't be grouped, then the next place you turn to is the P over Q. So what are my possible rational factors for this cubic polynomial?
P is 17, right?
Plus or minus 17, which means plus or minus 1 also. Those are factors of 17. And what are factors of the denominator?
Plus or minus 1.
Okay, so what are my two possible factors? 4, actually.
Plus or minus 17, plus or minus 1.
Now what do I do? I find it quite interesting that these numbers here don't have any bearing on the rational factors. In other words, doesn't it seem strange that we can change these numbers and that these are still the only 4 possible solutions for a rational solution? How do I test to see whether or not those are, in fact, if one of them is a 0?
Divide.
Okay. How?
Synthetic division.
Okay. What goes in the square? What am I going to test first? And what goes up top?
1. -2, -9, 17.
What should I test first?
1.
I'll point, you tell me what goes there.
1, 1, -1, 1,
-1.
-8.
Hold on, -1 here, which means -10.
-10.
I'm going to put an X there because it's not 0. If 1 were a solution, then that would have to be 0. So what should we test next?
-1.
Okay, I know you know how to do it, so I'll do it. Again, -1 doesn't work. $17. Oh dear. I had to make up a number like 17, huh? Let's see, that's 150 and 105. That's 255. Clearly, this is going to be like 246. That's going to be gigantic. Again, not. Well, I'm finding this a bit curious because I've always assumed that there has to be a rational solution. Maybe there doesn't. That's going to be like 240. So this is going to be like 205. Again, a giant number. Again, no 0. Put this into Wolfram Alpha. I'm kind of curious about it now. Maybe you see, my problem is that if it can't have strictly complex solution because they come in pairs, and it can't have irrational solutions because they come in pairs. So how do you not have a rational solution? We will see in a second here. All right, did I type it in right? There are 2 zeros and 1 0 at -3. Oh no, not at. It's actually -2.96. Well, that appears to be 3 irrational solutions, which I find a bit interesting. I'm not sure how you get 3 irrational solutions because I thought irrational solutions came in pairs. I'm going to save this one and study it more. But anyway, this is one I made up, so this isn't really one out of the book that we should be spending too much time with, although it was somewhat instructive. All right, let's try something else out of my book. Does this look familiar? What would you call this expression?
Completing the square.
No, we don't need to do that. Although if you want to go over some completing the squares, we can. But this is a quartic, so we would expect there to be 4 solutions. But notice that it's also very similar looking to difference of squares. And in fact, it is difference of squares. It is the difference of perfect squares. Notice that this number here is a perfect square, the square root being 9x squared. This number here is a perfect square, the square root being 4. So I can say this is 9x squared minus 4 times 9x squared plus 4. The fact that it's a quartic doesn't prevent us from using difference of squares on it. And now, notice something else. What do we have left?
Nothing.
Well, we have a difference of squares there, and we have an irreducible quadratic there. This one is going to give us imaginary solutions. I could solve this by setting this equal to 0 and doing it in a normal way, which we can do that, or I can say that's difference of squares also. So that's 3x minus 2 times 3x plus 2. This one, that's the sum of squares. Sum of squares does not factor down. So I have to leave that in this way for the moment. Alright, now I have it like this. What's my next step for finding the zeros?
I don't know.
We have 3 things multiplied together that are equal to 0. What does that mean?
Isn't it 3 zeros?
Well, it means any of them must be able to be 0. Because you can't get 0 from the product of 3 things unless one of them is 0. So it's the same step we would take with a quadratic. Only with a quadratic you have 2 things multiplied together that equal 0. So here we have 3. So we start out 3x minus 2 equals 0. Solve that. 3x plus 2 equals 0. Solve that. And 9x squared plus 4 equals 0. Solve that. That is going to give us our 4 solutions to this problem. What's this one? How do you solve this first equation?
X equals 2/3.
Second one?
X equals negative 2/3.
And the third one?
X equals square root of negative 4 over 9.
Plus or minus?
Okay.
Square root of 4 over the square root of 9. Negative 4, like you said. And let's simplify that. First of all, what's the square root of negative 4?
2i.
And the square root of 9?
3.
So there's our 2 of our answers, which are imaginary, and 2 that are real. So knowing that, if I were to graph this, how many x-intercepts are we going to have?
3.
We had 2 real solutions and 2 imaginary solutions. Imaginary
4.
solutions do not cross the x-axis. So we're only going to have 2 x-intercepts for this quartic. We're not going to have 4, even though we have 4 solutions. When you're looking for zeros of a polynomial, the only zeros you get are the ones that cross the x-axis. That's the only place y is equal to 0. The other zeros that are imaginary, well, I guess they count as zeros also, but they're not x-intercepts. So I guess there's a difference between asking for the zeros and asking for x-intercepts. The only x-intercepts here would be 2/3 and minus 2/3. But these would be called zeros for sure. All right. Are these problems too difficult? Should we go back and work on more basic ones or not? Are these what you wanted to cover?
I just don't really get them a whole lot. They don't make a lot of sense.
Which ones didn't make sense? The grouping?
Yeah.
All right, let's do another grouping. Because that's the ones you're most likely to get, are grouping ones. I would think that if they're going to force you to solve a cubic, they're not going to do it by making you use P over Q. They're more likely to do it by forcing you to do grouping. This one can be grouped. Why? What do we require to be able to group a cubic? You need the ratio of this number to this number to be the same as the ratio of that coefficient to that number. Is it?
Yeah.
Okay, that means it can be grouped. So, we're going to group the first 2 numbers together and factor them, and we're going to group the second 2 numbers together and factor it if it needs to be factored. So, let's take those 2. What's the greatest common factor you can pull out of there? Just those 2 terms.
10x squared.
Okay. What's left when you factor those out?
X plus 2.
Okay. Now let's take this. I'm going to put parentheses around that, but that doesn't change anything. Now, if this was a single term called y, you would have no problem with factoring it out, right? In other words, if I gave you this problem, can you factor that?
Yeah.
What's it factor to?
10x.
No, factor the y out. What's left?
10x.
10x squared plus 1. Okay? So, this is what you've been used to doing for the last 3 years in math, is factoring single terms out. but there's nothing that says you can't factor double terms out. This is a binomial term, this x plus 2. In fact, if it was helpful, we'd make the substitution. We'll let y equal x plus 2. We'll substitute y, then we'll factor it out, and then we'll resubstitute x plus 2 back in. But those two steps aren't really necessary. The only thing that's necessary is that you realize that this entire term can be evenly divided by x plus 2. This entire term can be evenly divided by x plus 2. So I'm going to factor out the x plus 2. When I factor the x plus 2 out, what am I left with?
10x squared plus
Okay.
1.
There you go. 10x squared plus 1. We have just factored this thing down to, now this is called an irreducible quadratic because it has only imaginary solutions. So if I'm factoring something down to its basic factors, this is where I'm going to stop. I stop when I get to an irreducible quadratic. If I could factor this further, I would. If this was 10x squared minus 1, I could factor it further. But since I can see that it has to have imaginary solutions because this is always a positive number and you add a positive number to that, this whole thing has to be positive. It can never be equal to 0. But that's grouping. I'm going to try another one or go on to something else, okay? These only work for well, you know, they might work for something else. I've only always done them with cubics, rather. I've never seen this applied to a quartic or a quintic, although I suspect that there probably are some fifth degree functions where you could apply grouping, but you're not going to see them on a test. But you might see these on a test. So why is this a candidate for grouping?
Because we have the same ratio.
Which is what?
2 to 5.
2 to minus 5 is the same as 18 to minus 45. And that's important. If I were to make that a plus, then you can't group it. You see why? There's no way I can end up with a same binomial term. But as long as these are opposite signs, in other words, these are both negative, they're the same ratio. Okay, so what next?
Factor out.
Okay, from each group. It's called grouping because we've made two groups. So what can you factor out of this group?
X squared.
Leaving
2x minus 5.
And what can you factor out of this group?
9.
Leaving
2 minus 5.
no 2x minus 5. It's critical because these two things have to be the same for me to be able to now factor that out as a binomial. If this was 2x minus 4, I'd be nowhere. I couldn't do anything more. So what's the last line?
2x minus 5. x squared plus
What about
9.
that? Yeah. In other words, when we divide, this is the answer, but the way we got it is we divided this by 2x minus 5, and we divided this by 2x minus 5. And what we were left with was x squared plus 9. That's grouping in a nutshell. Still confused?
A little less, but
Do we need to do more?
no.
Grouping? Okay, we got about a half hour. What else should we work on besides grouping cubics? How are you with quadratics? Can you factor any quadratic that I give you?
I don't know.
Yeah, we better make sure you can. Because that, for sure, is something you have to be able to do. You have to factor, or do you have to know difference of cubes and sum of cubes?
I don't think so.
Okay. So you don't have to know how to factor that?
I don't think so.
Okay. And I'm looking for some quadratics that we can practice factoring. Graphing, evaluating, and graphing. Why is this not instantly available to me? Gosh. Hold on, I gotta go back and look it up where I can find this. No wonder I wasn't anywhere near far back enough. Okay, so the problem here is to factor it or say that it can't be factored, and if it can't be factored, solve it anyway. Oops, I apologize. That's x squared. Makes a huge difference. So try to factor it.
Can't be factored.
It can't be?
No.
Well, how about this? In other words, that produces the correct middle term. When you said no, had you tried all combinations? In other words, you need to try a 3 here and a 1 there. And the only other combination is a 1 there and a 3 here. So there's really only 2 combinations to try on that problem. Sounds like this is where we should work. Is this going to be covered on your test, factoring quadratics?
Yeah.
Well, this is where we definitely should work then, because this, you might have 50% of your test be this. Okay, so let's go through this step by step, Silas. Don't try to do the whole thing at once. Tell me what to put in this spot, tell me what signs to use, and then go from there. So what goes here?
3x.
What goes here?
X.
What are the signs I need to use?
Plus.
Plus, plus. There's two signs. And now what? What are the factors of 10?
5 and 2.
And?
10 and 1.
So let's try them. Let's randomly try them. Let's try 5 there and 2 there. Does that work?
No.
Let's switch them. See if that works. 2 there and 5 there.
No.
Well, don't say no so quick. That's 2x. That's 15x. They add together to be 17x. What are you doing when you said no? Why did you say no?
Doesn't it have to, like, multiply to 10 but add to 17?
No, forget all of those rules. When you get different coefficients, when that 3 is different than that 1, you got to throw all those rules out the window. Because of that, the only time you can ever use those rules if it's x times x. In other words, if it's a situation like that, then you can use some of those rules, that factors of 10 that add to 17. But the moment you introduce a coefficient larger than 1 in front of either of these terms, even if it's 3 and 3, I can't say that anymore. It's just trial and error at that point. In other words, the moment I get to this step right here, then I just want to start listing all the factors of 10. There's 5 and 2, there's 10 and 1, and then I just go to town trying them as quick as I can. And if none of them work, then I know it can't be factored and I got to use the quadratic formula. That's the process with quadratics. It either can be factored or it can be solved using the quadratic formula. So the first step is really to determine whether or not it can be factored. I mean, actually not. You could start right out with the quadratic formula. It's just most people would rather not. They would rather try to factor it, because if it's factorable, it's much easier to factor than it is to stick it into the quadratic and solve it. Okay, tell me what to do.
8x.
I'm going to make a suggestion. 8x and 1x might be correct, but in general, in Colorado, they give you problems where the two closest factors are the answer. So I would always suggest starting out with 4x and 2x. Don't go for the extreme, further separated factors, and that includes over here also. In other words, start with 3 and 3. Don't start with 9 and 1. I may be wrong, but let's see what happens. Okay, what's the next step? To assign the signs. What are the signs going to be?
2 addition.
The signs, plus plus. Okay, and now we'll try 3 and 3. Does that work? Just multiply the insides, multiply the outsides, add them together, and it comes out to be 18x. So knowing to try the two closest factors is a huge shortcut, because if we'd have tried 8 and 1, we'd still be working on the problem. Because we might have tried 3 and 3, that wouldn't have worked, and then we would have had to try 9 and 1, that wouldn't have worked, then I would have had to go back and try 4x and 2x. So knowing, always start with the two closest factors would be my advice. Here and here.
5x and x.
Signs?
Minus minus.
And we only have two choices. We can either put what here and here, or the reverse.
2 and 1.
2 and 1 works. The inside's minus 2x, the outside's minus 5x, minus 7x. Okay. Solve that. Can't be factored. You're going to have to be able to do the quadratic on this test?
Probably.
Are they going to give it to you?
Probably not.
Okay, well, solve this then. Probably behooves you to write out the general formula first and then to substitute, rather than trying to do it unless you're really familiar with it. I mean, once you get used to doing quadratics, you don't need to do that. But it sounds like you're not that familiar with it. So let's write out the general formula, and then we'll substitute.
Negative b plus or minus square root of b squared minus 4ac all over 2a.
Did you do that from memory, or did you read that?
That's in my notes.
Thought so. Okay, now let's substitute.
7 plus or minus 49 minus 60 all over 10.
Okay, hold on. So now what?
X equals 7 plus or minus the square root of negative 11 all over 10.
Okay. Notice that by just changing one number from a 2 to a 3, that all of a sudden I have an imaginary solution. In other words, I don't have a real solution anymore. I have an imaginary solution. And what is that?
I don't know.
Well, let's put our i's in there. What's root minus 11 equal to?
I root 11.
Uh-huh. Well, I'm going to write it like this. for a reason. Now, that's an answer, but that's not in A plus BI format. If they want their answers in A plus BI format, how do I change this into that? Split it into two fractions.
Okay.
What's the A part?
7/10.
And the B part?
Root 11 over 10I.
Right. Now I really separate the I. Okay. Let's do more factoring, I think. I can't imagine what else would be as good a practice as factoring. Now watch, you'll take the test and there won't be any factoring problems on it. Should I start with?
3x. 2x.
Signs?
Minus minus.
Possible solutions.
5 and 1.
Does that work?
Yeah. No.
Hold on. What?
It doesn't.
Okay. So the only other possible solution?
1 and 5.
Does that work?
No.
Okay. So now what? It didn't have to be 3. Yeah, exactly. Let's try 6 and 1 because none of the other ones worked. So we still limited to 1 and 5, and clearly we don't want the 5 over there. That's going to get us up to 30. So we try the 5 there and the 1 there. Does that work?
No.
Okay. So we've just proven it can't be factored because we've tried all 4 possibilities. So immediately, without looking at your notes, because you're not going to have these notes, do you get a cheat sheet on your test?
No.
Okay, so you got to do this from memory. Now is the time to practice, not tomorrow in the test. So apply the quadratic to this.
B.
It's minus B.
Minus B. Plus or minus square root of B squared minus 4AC over 2A.
Good. Now that sounded like it was from memory. Now plug it in.
X equals 9 plus or minus 81 minus 96.
4 times 6 times 5 is 120.
4 times 6.
4 times 5 is 20. 20 times 6 is 120. So let's simplify it.
all 12. Negative 1939.
More simplification.
X equals 9 over 3/4
That's fine. Go ahead. Yeah. Okay.
plus or minus root 39 over 12I.
Beautiful. All right. I'm just randomly picking problems from my chapter. I don't know if they factor or not. It's in a section on saying whether they factor or not. What shall I try?
6 and 2.
Are there two factors closer together?
3 and 4.
I would go with that. You might be right with your 6 and 2, but my experience is that it's usually the closest factors. Now what? What are the signs going to be?
Plus minus.
Or
Minus plus.
notice that they are different. If the coefficients are the same, all I need to do is write a plus minus, and that's it. No minus plus. Hold on a second. But if those coefficients are different, then a plus minus is not going to yield the same results as a minus plus. So we have to allow for both. So at least we don't have that many factors of 7. What next? Should I try here and here?
7 and 1.
Good start. Does that work?
No.
And
Yeah, it does.
no, it's 21 minus 4, which gives you 17. So I immediately know that this doesn't work either, because it's the same numbers. It's minus 21 and plus 4, 17. It's just the opposite sign. So remember that. We don't have to try that combination. However, the other combination we didn't try is the 1 here and the 7 there. Does that work?
No.
Yes, it does. 3v minus 28v adds to minus 25v. So that's our solution. Did you test an hour-long test?
Hour and a half.
Really? Wow. We probably should have been having some hour-and-a-half sessions just to train your endurance. So what goes here and here?
2 and 2.
2W.
2. I'm changing it to X.
Okay.
And then
Signs?
plus, minus, minus, plus.
Actually, in this case, these two coefficients are the same, so plus minus is the same as minus plus. It would never make a difference. So I don't have to allow for both. Okay, how about factors of 27?
27 and 1.
Let's try closer ones.
Can't think of any.
About 3 and 9.
No.
Does that work?
No.
Almost, but not quite. Okay. Clearly, 9 and 3 aren't going to work. Because it gives you a big positive right off the get-go. So, is it worth trying 27 and 1? I guess it is before we go back and change it to 4W and W. But 27 and 1 can't possibly work because the moment I multiply 27 by 2, I'm way big. I'm 54. So that's not going to work, so let's try 4W and W, which is the only other possibility. And again, we'll try 9 and 3. Doesn't work. About 9 over there, 3 there. Doesn't work. 27 there, 1 there, doesn't work. The vice versa doesn't work. We've exhausted all of our possibilities. From memory, if you can.
Negative b plus or minus square root of b squared minus 4ac all over 2a.
Now plug in.
13 plus or minus 169 minus 16 times negative 47.
And is that a positive or a negative number under the radical?
Positive.
So our solutions are real. And we can see right away why it didn't factor, because we got a 13/8 plus something. So there's no way it had whole solutions. So we didn't make a mistake in factoring. And we don't need to do that arithmetic at the moment. Well, I think that was good. That was good practice. Silas, good luck on your test. This, I think, is our last session of the semester. And I hope to talk to you at the next semester.
Okay.
All right? Go get them. Bye-bye.